Hello, everyone. This talk will be presented by 4 people: project manager, graduate student in astrophysics, and 2 Red Hat developers. It is so for 2 reasons. At first, our objective can be classified either as complex or very, very complicated. It makes sense if it is explained by the subject matter experts. The second reason is that we think of ourselves as one team or equal team members. Therefore, presenting sequentially is our natural choice. We call ourselves VIGA project team, and that is according to STAR VIGA, which is photometric and spectroscopic standard, or was for quite some time. It is not used as a standard anymore, as recently it was discovered that VIGA is a fast rotator. This has a meaning to our project. We found that very apt, and that's to the origin of the name. Here's to the content of today's talk. Gabriel Szász will explain the inconvenience of quantitative spectroscopy. He will also mention the software codes and their ability for cloud-native environment. His successor, Filip Hubík, will walk you through our path, which led us to OpenShift. He will explain the challenges. We are trying to compile something which is not easily compilable. We are trying to parallelize something which was never meant to be parallelizable. Finally, Nikolaos Moraitis will explain why we use OpenShift. He will walk you through our pipeline, as well as explain the benefits of our approach. The benefits are something that I would like to elaborate for a second. I would like to explain what we perceive as a gap. We believe that there are many parts of science where which have the same gap, the same common IT denominator, and that is that scientists are not programmers. Scientists don't have necessarily the mindset to write cloud-native applications out of the box, or time to master such skill. This is usually closing the gap to the latest available IT technology, which usually is developed quite rapidly. This gap is not going to shrink over time. Our objective is filling that gap as a byproduct. With this thought, I would like to present next speaker, Gabriel Szász.
I mean, the only science case that we use for the VIGA project right now, and so far the only one, is the topic on my PhD project. However, I mean, specifically for this presentation, I'm not going to deep to the project. Instead, I'm going to just gently touch my PhD with explanation of quantitative spectroscopy and what is it about. Nevertheless, in order to understand the spectroscopy, that is, by the way, the cornerstone of modern astrophysics, and actually the reason why astrophysics became a field, I have to introduce you to the basic concepts of stellar models. So first of all, imagine yourself standing in a mist, and you can recognize the object in front of you, but as you are trying to look further, you can see less and less, and suddenly your eyes will see an impenetrable white wall, and you cannot see anything behind it. The same principle applies to the stars. And in case of stars, we are looking from outside on the gaseous ball that it consists of mostly of hydrogen and helium, and we can see through semi-transparent layers at the beginning, and it's getting denser and denser, and suddenly we cannot see anything that's inside. This opaque ball inside is called stellar interior, and there are we know that there are physical processes happening inside, but what happens inside stays inside. It never gets outside. So for us, as outside observers, the stellar interior behaves like a light bulb. It's an opaque ball which is emitting thermal radiation, and it's just backlighting the gas that's around it, and the gas around it is called stellar atmosphere. And it's actually the only part of a star that we can measure, that we can observe, that we can describe, and we can derive some parameters from it. As light passes through the atmosphere, it leaves traces in the spectrum. Like traces like these absorption lines here. And you would say, okay, by reading the absorption lines, by understanding the processes, we can immediately read the stellar parameters just both from the position and profiles of these lines. But it's not true. Stellar atmosphere has a structure like an onion. It has layers. And each and every one of the layers is adding more and more features, and they are blending over each other. So at the end, the resulting spectrum doesn't look like this. It's a mess. It's a forest of lines that are blending through each other, and we can no longer recognize their profiles. So how to analyze this? I mean, there has to be a way. And we figure out that the best way is to use so-called quantitative spectroscopy, the very first method that's developed over the last century. And we are going to do the inversion. We will set some initial parameters. We will guess them according to the other property of a star. Then we will calculate mathematical model atmosphere. And then we will try to ray trace this model atmosphere using the equation of radiative transfer. And we will get something called synthetic spectrum. Synthetic spectrum should match the observed spectrum in the ideal case. It doesn't, mostly. So, but after trying to fit it, we can try to tweak the parameters and reiterate it over again. And then over again, a process can take days, weeks, maybe months. If you think it's painful, if you think it's a nightmare, then welcome to my world. Yeah, astrophysicists are smart people. They often try to speed it up, try to find a way how to do it faster because they need to publish papers. I mean, we cannot wait like 1 year until we publish paper about the properties of one star. It's not feasible. However, we can construct so-called model atmosphere grids. We can pre-calculate the model atmospheres for a certain parameter set, and we can continuously cover the mesh of parameter space. And then we can just reuse the pre-calculated grids. This is usually done by supercomputers on the universities, and it takes maybe half a year, maybe a year, but after it's finally calculated, it's just placed online, and people can use it. And they don't have to recalculate it on their own computers. That's nice. That's a pretty nice idea. But usually, they are pretty static. Universities are not touching these grids anymore. Mostly people who've done PhDs on calculating these models, I mean, are already outside the university, they are somewhere else. And nobody is going to touch this because nobody really understands what's going on there, although the works are published. So what we can do? Can we make something like this but dynamic? Is it even possible? I mean, how much computing powers we need to this? And cannot we just put in the cloud and cloud will recalculate it over and over again and make it denser? Well, there is a problem. Most of the programs that are calculating model atmosphere were developed like 50 years ago, 20 years ago. Most written in Fortran or Ada or something very ancient. And this means that usually these are not parallelized because, long time ago people didn't tend to parallelize things because it wasn't possible. They're not scalable because they don't think about it. And they're not multi-platform, really. And according to user experience, do scientists really have time to tweak user experience? Probably not. And I'm not speaking about documentation. It's just, maybe there are a couple of people who can understand the code, but otherwise nobody can use it. So by moving these applications to the cloud-native environment, we can speed up the development process, we can make it more convenient, we can create a new front end, and this will not only change the way how we are doing quantitative spectroscopy, we can change whole fundamental science. And now I would like to invite Filip Hubík, who will tell you how we are going to reinvent the quantitative spectroscopy.
So at this point, we have a scientific problem. It's very well defined, but we actually need to do some work. So we need to figure out what we need to do. We need to compute as minimal viable output single model. And in the end, we need to compute the whole grid of these models. We need to add ability to easily recompute them, to do some data mining, to make people easily access it and use it. So we need to start with single model first. It's not as easy as it sounds. First, we need to, what we had to do is research. We try to figure out whether there is a tool that does exactly what we need it to do, but in the cloud-native way, which would be highly parallelizable and which could scale into current infrastructure limits. We haven't found such tool, so we figured, well, we may be able to actually program it, develop it from scratch. We tried on several layers of parallelism, even from low-level frameworks like MPI, Chapel. We tried OpenShift native OpenWhisk. We tried to go a little bit above that with OpenStack, and we failed every single time, not only on the scientific part, but on the implementation part. Since we are not full-time team, we are basically a hobby project. This would, by our estimate, take several people, software developers and scientists working together full-time for months, maybe even years. And even though it might be futile anyway, because it might not be accepted by the scientific community. So what we've done, we found tools that do some part of it, what we need, and we try to combine them and make them run in parallel in distributed environment. Some of these tools, for example, for computing models are Atlas and Lusty. Fun fact, one of them was developed in Los Alamos in 50s in Fortran, so you can imagine how hard it is to run today on current architectures. The other tools like SynSpec and Synth, they are used to generate synthetic spectra. They are usually written in archaic tools, in archaic languages like Fortran and Ada. They are hard to run on current architectures, hard to compile. They may not be even supported by current compilers. Even if we are able to compile them, they may still not be runnable in the environment, failing with mysterious messages, segmentation faults, not doing anything without any messages. They are usually poorly documented. They have some missing files. They are developed by scientists for specific and narrow use cases. So we try to parallelize them to do what we need them to do in our model. This is part what I call welcome to hell, because running these tools, running them together, and even integrating them in our model is basically hell on earth, but the good thing is it has to be done only once. Because of containerization abilities, we could do it only once and then run them as we need without going to hell again. So we did, as the last part of research era, we tried to do some numbers and we tried to figure out how long it would take to actually compute our full matrix, the whole grid, on one mid-grade server node today, it would take more than 2,000 years. We took it to the other extreme and we tried to figure it out if we had unlimited parallelism, how expensive it would be if there was such a cloud that would be able to give us the unlimited parallelism. We did the estimate for Amazon prices, and it took something like $1 billion USD in one computation cycle. So obviously we need to find some middle ground in our, let's say, with our resources. We need to develop something that is easily usable, it has to have unlimited scalability. It needs to have the ability to easily engage people into collaboration, public-private groups with certain interest communities, scientists. And we need also this whole solution on every level to be easily understandable. And it means people will not be afraid to reuse it and give another shot to their theories, change the input parameters, and easily compute. So after several frameworks we tried, we just decided we will use pure OpenShift because the bottom layer, the hell on earth, can be containerized and it can be shadowed from the logic. And the layer above, it has enough flexibility for us to implement our parallelization layer even there. So we will use all the features that I mentioned, and we think this is the optimal way how to go through this problem. So with that being said, I will pass on Nick Moraitis, who will explain the OpenShift implementation.
So the story goes now. We've been through hell, we burn our brain in debugging. Yeah. So, and now we know what we need. We need to develop an application on a cloud native environment. And what we need, what else? We need OpenShift, right? We don't have to care about other tools that we need to use to make our life easier. OpenShift has an embedded CI that we can use. We can easily develop our application there. And one of the most important things, resources. We don't care actually about what kind of resources we have. We need CPU. We need it now, right? So hybrid cloud, OpenShift is really flexible on that, so we can use every resource. Easy deployment. We might need to deploy the application in many clouds, in different kind of environments, and develop the application on OpenShift can actually give us the ability to easily deploy it everywhere. Okay, so we have everything ready and we can go to production. We need, well, actually the calculations as Filip explained, it can take like months, maybe a year, depending on the resources that we have. So we need to continuously monitor our stuff, and we can do that because OpenShift comes with Prometheus, metrics, and Grafana dashboards, alert managers, that we can continuously monitor everything. And we can expose Prometheus metrics within our application. So in general, we end up designing something like an application that we need to calculate all the data. So first, we need to understand the calculation pipeline, right? So the basic input parameters are the temperature and the gravity. So we create a Kubernetes object within the cluster, which gets this kind of input, and we distribute them in worker nodes. And basically, now we know exactly what the steps should be. We are using different kind of binaries that we have written in ancient languages from scientists, and we found the bugs, but we can't fix them, right? It's not our problem. And we have to compromise our application in order to work with that, right? So Atlas 12 is written in Ada. If you check the code, it's like 300,000 lines of no comments. in there. So some functionalities that we can't even debug because we didn't read the program. So we have to go through it. Atlas will run 2 steps actually. It will generate many files. We need to exactly pick up what files we need. And it will generate a stellar model, atmosphere model. So what this is, okay, this is a table of physical quantities that characterize one-dimensional stellar atmosphere as a function of radius. Okay, so if you guess that this is as complicated as it sounds, you're wrong. It's actually more complicated. I don't even understand it, so Gabriel does. And the third step is to create the synthetic spectrum, and we're using another binary written in Fortran, SynSpec 49. And basically this is to understand, it's actually a one-dimensional table as well, and to understand how photons are interacting with a stellar model atmosphere. Okay, this calculation will run in parallel in each worker node, and our application turns out to be something like this. This is the most simplified version of the explanation that we have to show. Okay, so with OpenShift, we have a development environment that we can just go through production and we'll solve the bugs in real debugging when the calculations are running. So basically the master nodes that will host the actual application will run many services. One of the services, the main service is the dispatcher, which read the database. Database will hold all the information about the calculations. I will try to be quick because we are out of time. There are other services. One of the most important services is the front end, because scientists will actually work on that. Everything is going to end up in a big storage. We estimate that we need around 100 terabytes. So, and all the results will be there, and we'll take a part of the grid, and that the sizes we're going to use. And the worker nodes basically are the nodes that we are going to consume the whole CPU, and we need as much as possible. So it's we can do it like with VM instances, with bare metals, power PCs, whatever is joined in the cluster. So basically, this is a basic idea how the front end should look like, because we need to make this to be flexible for scientists, right? As Gabriel mentioned before, that we don't want for the grid to be calculated and be static on the internet, and scientists just use it and they can't tweak it. The main concept is that once we first create the first model, scientists all over the world will be able to tweak the model, and by time to time the model will be grow, and it will come with different variations and more data, and this is going to be in collaboration all over the world for all the scientists. Okay, so just to make a closure here, because we're out of time. Sorry. I want to mention that we will be able to do any of that without OpenShift, and this is the most important tool that we are using right now. And I would like to thank everybody that he co-recruited in the project. Also, I would like to thank Radek Vokal that he was able to make some collaboration with the universities and get some resources. One other thing that I would like to mention is that if you have resources and you need to give it to us, we are most welcome. And thank you very much. Any questions?
Questions?
So thank you very much for interesting talk, and I'm very interested in what were the typical issues with the ancient code. So what, if I'm now going to port some ancient application, what I will typically face?
So basically, these applications were written by scientists, and they didn't even know how to create a development. It's like I'm a developer, but I need something to do on my computer. Just create a script, you know. And that will come with many problems, with many bugs. For example, we have a bug that it couldn't read a space in a file that was like 1,000 lines, and one space was different inside this big file, and the application wasn't able to work, and we didn't know why. It's no. The implementation details, it's like they are parsing files instead of flags, and actually the languages are really ancient, and we need to compile them, right? In order to make it work in a cloud environment, in containers inside, for example, in PowerPCs and different architectures and stuff like that. So our plan, and it's nice that you made this question, our plan is to rewrite this kind of programs in the future in more modern languages like Julia, which is like really good languages in calculating and running calculations. And we're expecting students to do that, right? Because they are working on that, and this is their responsibility for the scientific community, right? So we expect to have some interest in order to do that, but in the future. So.
Thank you very much.